Now for the CNC software that we use MOX-free CNC software because it's open source, because cost is important, and it's also one of the very few that run on Windows XP. It's able to control up to 6 axes, but right now we're only using 1. So in future development of this project, we'll be able to do more elaborate things. And also, this is what it takes the G-code, as seen up at the top in the top picture. It takes G-code and transmits it into steps and direction signals and sends it out to DB25 parallel port. Now here's the overall circuit design of the motor control system. We have 2 limit switches for the max and min, the stepper motor, and the driver board, and then the PC. There's 2 power supplies because the 12 volt is used to power the limit switches and the driver board, and the 5 volts needed for communication between the driver board and the PC. Now we're going to show a demonstration of our 3D printer in action. Now Bryan is going to discuss some administrative matters.
Okay, so you can see from the video, the outcome wasn't quite what we were hoping for at this stage of the research project. There are some things that we need to look at, problems encountered along the way. Part of it is the actual mechanical building of the transducer, which has a booster and a sonotrope tip on it. Those need to be actually tuned to the exact frequencies, and that requires some finite element analysis software, which we would be able to do in the second phase of this project. As ECE students, problems we encountered, power supply design. The first 3 designs that we built did not produce the power needed to drive the sonotrope, so we did go through several designs before we got to that. Motor controls is just more of learning the motor controls in general, and the bandwidth products of the amplifiers being able to operate in the frequency ranges we needed. So lessons learned. We had to learn a lot about different things. Piezoelectric elements, which is what the ultrasonic transducer is, and how to drive those, which is part of the power supply. So we've got power requirements for those. We also have safety since we're dealing with a higher voltage and current. The instrumentational amplifiers, the microcontrollers, and integration with the sensors are all different things that we encountered over the course of this semester. The learning of how to drive the stepper motors using the CNC software and the limit switches all integrated together was part of that also. We had to do system integration with the mechanical parts, obviously, and the electrical parts. And overall, just learning how to use different machinery within the shop, building our own parts, using a milling machine, using a drill press, and different things to build our parts for this project. So the total cost, as far as time-wise, that's just the hours we put into what's here. That's not the extra time that we spend in research. That's just a figure there that's on what's on the card here. We were able to get a lot of sample parts and different parts donated to us. So the cost of $325 we didn't actually spend because we were able to get samples from Texas Instrument and Fairchild and other places that would provide those to us. So the purchase parts here were $253 on our cost. So I'd like to give a special thanks again to Mr. Nergis. He did a lot of the mechanical design of all of this is built by him. The idea was thought of by him, and he also provided electrical engineering background, providing information and guidance throughout the semester. Professor Packwitz for being our faculty supervisor, keeping us in line. Professor McCoy gave us assistance on the power supply design. Professor Beatty was involved in last semester's proposal, and Professor Kreshman from the physics department who allowed us access into the shop to do this work. Thank you very much, and we'll open it up for questions.